This is problem number 3, a problem that I spent a very long time thinking about because I was bothered by the way this equation is written and by the way the stories go with this equation. So I'll get into those details in a little while. But first, let me solve this problem the way I think the authors intended for students to solve it. So I'm going to look at it. So you have two stories, and you're supposed to match which story matches this equation. And so the first story is about temperatures changing in recording stations, 2 recording stations in Antarctica, so it's cold. So at one time, at 5 o'clock, the temperature at one station is -6 degrees, at the other station is 2 degrees, and then those temperatures change over time. And after 3 hours at one station, the temperature reads the same as at 4 hours in a second station. So the times are different, but the temperatures are the same at those 2 different times. So that's one story. So does that story match this equation? Or the other story is 2 students are playing cards, Elena and Kieran. And Kieran starts out with a -6 points. Elena starts out with 2 points, and they collect 3 pairs and 4 pairs. They collect a certain number of points per pair, and at some time during the game, after Elena collects 3 pairs and Kieran collects 4 pairs, they have the same number of points. So different pairs of cards, different numbers of pairs, but eventually they have the same number of points. So first of all, you just look at the numbers. So the starting values for the temperature is -6 and 2 degrees, and the starting number of points for the card game is a -6 points and 2 points. And right away you see that Kieran has a -6 points. That's weird. In the card game, you're going to see that they earn a certain number of points per pair. Those points are not negative. So how does Kieran get negative points? So more than likely, story B does not match this equation, and story A does. It's understandable to have a negative temperature. It's not understandable to have negative points in the way that this game is set up. But if you continue, this is 3 hours and 4 hours. So this is the coefficient of this variable here. The number that goes with this variable is 3 hours, or in this expression, it's 4 hours, or 3 pairs and 4 pairs. And so now if you solve for the number of degrees per hour, it says x is the constant rate, the degrees per hour. So if you solve for the number of degrees per hour or the number of points per pair, x is the number of points per matching pair. So solve for x. Now these are the kind of problems that we've been looking at. So if you have an equation with an expression on each side that has a different value next to the variable, so that's called the coefficient. When they have different coefficients, and we've been graphing these, that means they have different slopes. That means that these two lines, if you graph this as a line, a linear equation, and you graph this as a separate line, a separate linear equation, both equal to y, which you can do, then you're going to see that those lines will intersect where this value, where you solve this equation for that value of x right there. So if you do that, you're going to get the same temperature. X is going to be, actually then you replace that value, whatever you come up with the value for x, then you replace it in either side, and you're going to figure out the same temperature or the same number of points. And here's the constant rate. Once again, that's x. Now this is different than what you've had before, and this is why I started to get bothered by the way this problem was written. What we've had up until this point in time, and I've separated these out and I've written separate linear equations for these, but the coefficient is usually the rate. It's how much y is changing per value, per unit x. But here they're saying the constant rate is x. That doesn't make much sense to me, and I'll go into that in much more detail in a few minutes. But let's graph these two sides, these two expressions, as separate lines for a moment and see what we get. And right away it starts to seem odd the way you set it up, but that's okay. I don't have a problem with setting up the graph based on just this equation right here. But what you notice is if you start out at -6, this is the y-intercept -6, and the slope is 3. If I go to the right, I'm going to go over 1 unit and up 3, over 1, up 3. If I go to the left, to make this a positive slope of 3, I'm going to go 1 unit to the left and 3 units down. 1 unit left, 3 units down. So that'd be a -1 over a -3. I'm sorry, -3 over a -1, which gives you a slope of a +3. On the other hand, the other side gives you this expression and this equation. So this has a slope of +4. Now notice this is starting out lower than this point. So this is starting at -6. This is starting at +4. This is a lower slope. So it's going up slower than this line right here. So these lines in the positive direction will never intersect. They will get farther and farther apart. So you have to realize, at some point you realize when you're constructing this graph, that you have to go backwards. You have to go in a negative direction to find out where they intersect. So now you're going to solve this equation for the value of x. So you go out here to x. Where do they intersect? At what value of x? And actually, yeah, what value of x do they intersect? So you solve for x and they intersect at -8. And then you replace either side with -8 and you're going to get the value, the y value at which they intersect, which is -30. So -8 degrees. So the first story is a -8 degrees per hour. At 3 hours and at 4 hours, you're at -30 degrees. So 3 hours on this side, so 3 times -8 is -24, plus -6 is -30, or 4 times -8 is -32, plus a +2 is also -30. So you can use either side, yeah, to solve to get the number of degrees in this case. In story B, it's a -8 points per pair. So at 3 pairs and at 4 pairs, both players have a -30 points. And that doesn't make any sense. I mean, you can set the game up so you accumulate negative points, but it just doesn't make sense. You would never do that. So really the story that matches the equation up here is story A, the one about temperature. Now you start looking at this graph, and I started to realize, well, this is just weird to graph the change in degrees per hour on the x-axis. So you graph the number of degrees versus the rate, the change in degrees per hour. And that this line here is actually for 4 hours. This line here is for 3 hours. But you're looking at them as a rate. This is the slope. That's how much this line changes per these values up here. And so now I'm starting to get all befuddled and confused about how do you interpret this graph. Now the author has never intended for students to go to the point of graphing and interpreting the graph. They just intended students to, as far as they were going to go, probably would be to solve the equation, get -8, but not interpret that within a graph. So the rate is -8, and then you plug that into either side and you get a value of -30. But there's nothing to prevent students to go beyond that and graph it and try to interpret it. But that interpretation, that story that would go with this graph is really beyond the scope of this course. It's really a 9th grade problem, or I don't know when students begin to look at those problems. But let's go on for just a second. So what bothered me was the way the story was written. So I rewrote the stories, and so we're gonna go back and forth. I rewrote the stories. So this is where you could end now. You could stop this video now, but this is where I really get into some detail that I thought was interesting. And so how could I write this story better to lead the students in a I think a better path to understand what's going on. So I rewrote the story. So this is the temperature story. So 2 weather stations. The temperature changes at the same constant rate, m degrees per hour. I even have a problem with this, and I'll get into that later. Throughout the night at both locations. So now I'm very specific. The temperature at the first station is 3 hours after its first recording, so x equals 3. The second station, x equals 4. And I'm changing the variable up here from x to m. So if you go back to the original equation, it's y equals mx plus b. So I'm changing the rate to m. So that's more consistent than what we've worked with. Now this is unusual. The students haven't seen a problem where they have solved for m. They've seen a lot of problems where they solve for x, but no problems. I don't think there's been a single problem where they've had to solve for the slope. But let's go ahead and look at that. So the constant rate, m degrees per hour, and x is equal to 3, x is equal to 4. So in this case, you can solve for m, and you're going to get a value of a -8 for this slope right here. And to interpret that in a graph, to draw the same graph that we just looked at, again, it's really beyond the scope of the course. But you can use that. -8 is the common slope, and then rewrite the equation using x and -8 as the slope. So this is -6 plus -8 times x. So on this side, that x is going to be 4 hours. 2 plus -8 times x. On this side, that x is going to be 3 hours to make them equal on both sides. But notice this goes back to some problems that we've just been working with. When the coefficient of the variable is the same, then there is no solution to the, and the y-intercept, this constant out here is different, then there's no solution to this equation. They are parallel lines. They go through the y-axis at different places. They never intersect. So this goes back to the problems that we've looked at where there's a single solution for the equation, there are an infinite number of solutions for the equation, or there are no solutions for the equation. This is the example where there are no solutions for the equation. So if you solve it, you're going to get rid of this -8x on both sides, and you're going to end up with -6 equals 2, but they are not equal. So there's no solution. When you graph it, you're going to come up with parallel lines. They will not intersect. There will not be a time when the temperatures will be the same. So there will not be a same time when the temperatures will be equal. So station number 1 is at 3 hours out. So 3 hours times the -8 is -24. Add them together, you get -30. Station number 2 is 4 hours out. So notice this is starting at 2 degrees in positive 2 degrees. And so this has to go farther to get to -30 degrees. This is starting out at -6 degrees, so this doesn't have to go as far. And notice that the difference between that -6 and 2 is that 8 degrees. This station has to go 1 hour further because it has 8 more degrees to catch up to station number 1 to get to -30. So again, this is getting pretty complicated. But a graph of them, so now I can graph each of those lines separately. This is 2 plus -8 times h, the number of hours, or -6 plus -8 times h, the number of hours. So this is the graph for station number 1 is right here, and the graph for station number 2 is right here. So at what time, so at 3 hours, station number 1 is at -30 degrees. And so when is station number 2 at that same -30 degrees? Well, that station number 2 has to go another hour. Remember, it starts out 8 degrees behind. So this is a positive 2 degrees, -6 degrees. That's a difference of 8 degrees. It's going down 8 degrees per hour. So station number 2 has to go 1 more hour. Let's go out here 1 more hour for the temperature to go down 8 more degrees. And so to be at that same negative 30 degrees. So this is 4 hours, negative 30 degrees. So now this makes sense. This is consistent with what students have done up to this time. So station number 1, negative 30 degrees after 3 hours. Station number 2, negative 30 degrees after 4 hours. Still a complicated problem, still difficult, but consistent with the thinking of the course at this time. All right, so the story with the card game. So m is the points per pair. So I like this way of stating this better. So m, the slope, is equal to the points per pair of matching cards. You could even say y points, so the y value. Y points per pair of matching cards. And x is 3 pairs or x is 4 pairs. Again, solve for what the number of points per pair of cards is, which is the slope, or m. You can come up with that same negative 8. Come up with the same equation. Cannot be solved. There is no solution. So you're going to get the same graph. So Elena collects 3 pairs of cards to get to negative 30 points. Kieran collects 4 pairs of cards to get to negative 30 points. So it's going to be the same graph. This story does not make sense where they collect negative points, but you're going to get the same graph. This is Kieran, I believe he's at negative 6. This is Elena, who starts out at 2 points. And at what number of pairs do they have the same points? Well, for Kieran, he has 3 pairs because he's starting at negative 6. Elena has to collect 4 pairs because she's starting at 2 points. I think it's, let's go back and check for just a second. Elena, yeah, is at 2 points. All right, and Elena collects 4 pairs to get to that same negative 30 points. So the story doesn't make any sense, but the graphs are the same. All right, so now I want to go through the story. What bothered me about this and why spend all this time? So the temperature changes at the same constant rate. And so I feel much better about the problem if they change it to be consistent with this general form of this equation, of a linear equation. Y equals mx plus b, m is the slope. So just the simple change of changing x to m, and out here x to this m, that's a lot better because now I can understand that this is going to be the rate, and I'm going to put different times in here for x. So I'm going to put 3 hours and 4 hours. So if you go through and solve, you're going to get negative 8 degrees per hour, and you plug that back into the equation. So for 3 hours, you get negative 30 degrees, and if you go back and use the other equation, 2 is this equation right here, 2 plus 4m. So put negative 8 right there, you're going to get negative 30 degrees for 4 hours. So station 1, 3 hours, negative 30 degrees. Station 2, 4 hours, negative 30 degrees. This is the same stuff. But then I go on to the card game problem. And this is where I really start to have some difficulty. So I look and okay, I'm going to change that to m. That feels a lot better. That's the slope. This is 3 as the x value. Usually wouldn't do that, but 4 as the x value. And it's okay up until now. So let's get rid of all that other stuff. So then I look 3, so I change x to m. But then I looked at this x right here. What is that x right there? It's x points. But this x up here is points per pair. So this x, these two x's are points per pair. This x is just points. Well, you can't have that. You can't have an x be two different things. So I'm going to change, this is actually y points. So you collect a pair of matching cards, they earn y points. So it's y points per pair is the slope. So change this x to y. So it's y points per pair of cards. Now this is getting really tough to follow. I understand that. And it'd be nice to have a conversation with a few people to come to some conclusion about how to present this problem. But notice that this x is different from these two x's. And just as a language issue, if you're teaching students who are learning English as a second language, you have points here. That's a different definition of points. And you have at one point here. That's a moment in time. So it's using a different definition for these two words, these two points. So you want to stay away from that. So I rewrote the problem to stay away from that. All right, so I went back to the first problem and looked at this a little bit more, and I struggle back and forth. Is it better to change this to y or to leave it as m? And I don't think it really matters very much. It's probably more consistent to change it to a constant rate. You should say constant rate m equals y, right here. Constant rate m equals y degrees per hour. That's probably the best way to state it. You want to make sure the student understands that this is not the y coordinate. This is the number of degrees that are changed each hour. So it's not the y coordinate at 1 hour, but it's how much y changes each hour. So students right now are struggling with this idea of slope, rate of change, rate. What do those things mean? And they have to distinguish those from the coordinates on a graph in an xy pair. So the graph, the issue is to lead students to drawing this kind of graph. Oh, actually, I wanted to cover this idea of slope just a little bit more using this point right here. So the slope is not y over x. It's not -6 over 1. It's the change in y. It's how much this y has changed during this 1 hour. So this change has been 8 degrees. So the temperature has changed to -8 degrees in that 1 hour. So in 1 hour, it's changed 8 degrees and -8 degrees. This is why we worked with the slope triangles and slid these slope triangles to the origin, so that now when we draw the point using the slope triangle, this is truly 1 and this is truly -8. And because it now goes through 0, 0, the y-coordinate is the length along the y-axis, and the x-coordinate is the length along the x-axis. But in the beginning, it's not. So you have to find the difference. So this is a -6 minus 2. So this ending point minus the beginning point is going to give you this -8 degrees. And this ending point, 1 hour, minus the starting point, 0 time, is going to give you that 1 hour in time. So that slope is a -8 degrees per hour. So at every common value of x, they are 8 degrees apart. That's why you have to go an extra hour to gain that extra 8 degrees to be at the same temperature. Again, interpretation of these graphs has gotten tough. But the issue is to lead students to this kind of graph, these two graphs, versus this graph. This graph is difficult to interpret. Now, students can solve the equation, and I would just say, as a teacher, I would just say the graph of this equation, I might even put it up on the screen, and say the interpretation of this graph is for a later time. It's a course in 9th grade, just later in time where they are. So you want to keep them away from this graph. Now, there is a context in which these graphs do start to make sense. So now I'm really getting out there. And that is a distance time problem. So if distance is equal to the rate times time. So it's the speed that you travel over a certain time is going to give you the distance that you've traveled. So now if I graph distance as the y-axis, this is the kind of problem where you might look at the distance versus the speed and figure out at what speed do you have to travel to get out a certain distance. So -8 miles per hour is the common speed, and this is 3 hours, and this is 4 hours. So now I've changed the entire context of the problem to speed. And I'm going to write a problem that goes with this in just a moment. So imagine you have two cars, and they're both traveling at the same speed. So after 3 hours for one car and 4 hours for another car, so this is 4 hours and this is 3 hours, they are the same distance from point 0, this point right here. So what speed do they have to travel to be at that distance, that same distance, if one travels for 4 hours and the other travels for 3 hours? So you can solve for the speed, and it's going to be a -8 miles per hour. So -8 miles per hour, this goes back to 7th grade when we looked at negative and positive integers. If you're traveling west, that was negative. So this is traveling at a speed going west, and this is a distance going west. So -2 miles is 2 miles in the west direction at a speed of -1 mile per hour, -2 miles per hour, -3 miles per hour. So it's increasing speed going west as you increase the distance. So what this is saying is that each mile you're traveling west at a faster speed. I want to be at this point in 4 hours. To get to this point in 4 hours, I have to travel faster than this point in 4 hours. I want to get farther in 4 hours, or I want to get farther in 3 hours. So to get farther in a set amount of time, 4 hours, I have to travel faster. To get farther in that same set amount of time, in this case 3 hours, I have to travel faster. So how fast do I have to travel to get 30 miles away from my starting point? So let's look at this example right up here. Begin at 2 miles and travel west 4 miles. So I'm going to begin at 2 miles east and travel west 4 miles. That's a total, so from 2 miles east to 2 miles west, that's a total of 4 miles. And so what speed am I traveling? I'm going 4 miles in at 4 miles per hour. So I'm traveling at a speed of 1 mile per hour. I'm sorry, traveling 4 miles in 4 hours. So I'm traveling 1 mile per hour. Here I'm traveling 8 miles in 2 hours. So I'm traveling 2 miles per hour. So 8 miles in 2 hours. I'm sorry, 8 miles. 8 miles in 4 hours. So I'm traveling 2 miles per hour. 2 times 4 is 8 miles. So I've traveled a total distance of 8 miles. It's taken 4 hours to travel that distance. So what speed have I traveled? 2 miles per hour. So the interpretation of this graph is getting really tough. But just continue just a tiny bit. So I'm going farther in 4 hours. So if you look at this graph, you're going farther in 4 hours. You have to travel faster. So I want to go farther, this distance right here, in 4 hours. This is all 4 hours. So I have to travel faster to go farther in that 4 hours. So to get 30 miles out, I have to travel at 8 miles per hour. To get 30 miles out here, I have to travel at 8 miles per hour. Okay, what's a story that might fit that? At what speed, miles per hour, will two cars be an equal distance from mile 0? this right here. So two, same speed, but two different time points to get the same distance. It's a very tough problem to understand. So two different times, yet going the same speed. And here's a story that might match it. So you have two brothers that live at home. So mile 0 is going to be their home. And they're going to meet at a restaurant that's 30 miles from their home. But one brother, neither brother is home. One brother is 2 miles away from home. The other brother is 6 miles away from home, but 6 miles closer to the restaurant. The other brother is 2 miles away from home, but 2 miles farther away from that same restaurant. So at what speed do they have to travel if it's going to take one brother 4 hours to get to the restaurant and the other brother 3 hours to get to that same restaurant? They have to travel at 8 miles per hour going in a westerly direction. That restaurant is going to be west of their home. So one brother is 32 miles from the restaurant and will take 4 hours to get there. The other brother is 24 miles away and will take 3 hours to get there. So the other brother is going to get there. The one brother is going to get there 1 hour earlier. So he has to sit at the restaurant, listen to the band play, listen to music, do something while he waits for his other brother. This speed, by the way, is very slow. All right. I went way overboard in this. I know that. There's probably lots of points of argument that one could make with what I have said. It'd be an interesting discussion to have.